Okay, welcome everyone. Can you hear me? Can you hear us? People on the Zoom, can you hear us? Anyone? Can you hear us?
Maybe we
Yes?
can't hear them.
Yes, yeah. Great.
Okay.
So we are very happy to have Nishad Maskara. Nishad was speaking about some of his work on this enhancing detection of topological order by local error correction. Let me remind the audience, both here in person and on Zoom, please feel free to ask questions and interact with Nishad. And we also have a seminar dinner tonight. If you want to join us, send me an email, please. Okay, thank you. Please go ahead.
Okay. Thanks, Ruben, for inviting me to give this talk today. So I'm going to tell you guys about some of our recent work on how we can use ideas from error correction to actually improve the detection of topological order, really kind of geared towards detection of topological order in real systems. So, I'll start by discussing a little bit, what is topological order and why is it something we're interested in. So, one of the really interesting features of topologically ordered systems is that they have emergent gauge fields. So, as we all kind of learned early in our physics career in electromagnetism, gauge fields essentially are like Gauss law type behavior, where you have charged particles, and these charged particles produce field lines that you can detect by measuring like loop operators or operators supported on surfaces and things. Remarkably, in many condensed matter-like systems at low energies, you actually get this type of gauge fields emerging as like the effective description of the low energy systems. Another key aspect of these emergent gauge fields is that they induce strong constraints on the on the degrees of freedom in the system. So, for example, there's like a strong constraint that every time I have a charge, I also have a bunch of field lines coming out of that charge. So we'll kind of see today like some very microscopic systems where this type of behavior emerges at low temperatures. Another really interesting property of these topologically ordered systems is that they have anionic excitations, because in particular, we're going to be studying models in 2 dimensions. And so in 2 dimensions, when you have excitations, along with these emergent gauge fields, you can get quasi-particles that have kind of exotic mutual and substatistics. And one thing that I think is really remarkable here is that even in a model that's fundamentally just made up of bosonic constituents, you can get emergent degrees of freedom that actually have fermionic statistics. So, this is actually like a very interesting type of behavior, and understanding this behavior can actually potentially bias a lot of things when it comes to, developing and doing new physics. So, kind of more on the application side, some of the reasons why we're interested in studying and understanding topological order are, for example, useful applications like performing lattice gauge theory simulations. So many of the things that we're going to discuss today are kind of going towards performing useful quantum simulations of like lattice gauge theories and other things that appear in other areas of particle physics. There's also a lot of interest in using topologically ordered systems as a way to robustly encode quantum information. And in particular, there's this idea of using anyons and braiding as a way of doing fault-tolerant quantum computation.
You can actually see them.
No, it's okay. If I stand, it's easier to talk. Okay. Also, if anyone on Zoom cannot hear me, just please shout, spam the chat. Okay, cool. Good. And one of the reasons why we're especially interested in this type of stuff now is that for the first time, people are starting to be able to create these states of matter in the lab in very controllable quantum simulation platforms. So a lot of this stuff is going to kind of form the motivation, in particular this experimental realization for the stuff that we're going to discuss during the rest of the talk. So kind of more broadly, beyond topological order, a very interesting problem in condensed matter physics is characterizing different kinds of order. So a lot of our intuition about different types of order that can exist are built on top of what I'm going to refer to as RG fixed point models. For example, in the transverse fieldizing model in the symmetry broken phase, your fixed point model corresponds to the states where like all spins are ferromagnetically aligned. These states have no quantum fluctuations on top of them. And as a result, they have like essentially correlation length 0. They have no local quantum fluctuations. So they're very theoretically convenient. And actually we have like a very microscopic way of talking about excitations, and other things in these types of models. For those who maybe are more familiar, these are like, models with like commuting projector Hamiltonian, parent Hamiltonians. However, in realistic systems, you always have fluctuations, deviations from your perfect RG fixed point. So for example, if you take your transverse realizing model and you add a transverse field, then this will lead to like some spins spontaneously flipping. And this results in some finite correlation length at short ranges. And so these types of systems are definitely much more theoretically difficult to analyze quantitatively. In particular, finding the dressed operators is a difficult computation. However, they're kind of ubiquitous in experimental realizations. So understanding these systems and developing tools for characterizing and controlling them is kind of a very interesting question relevant to doing real experiments. And the tools that I'm going to discuss today, specifically this idea of local error decoration, is a set of tools that actually allows us to deal with these realistic fluctuations in realistic models. In particular, we're going to kind of cut our teeth on the problem of quantum phase verification. So specifically, imagine you have a quantum many-body system in some unknown state rho, and we're going to ask the question, does this rho belong to a particular phase? So, we have some input state that we measure in our simulator. We do some amount of quantum or classical processing on the state. We perform some measurements and then do some more processing. And at the end, we should get out some classification, And in particular, we're going to output 1 if the state is in P, only if the state is in P, and then we'll output 0 otherwise. So 0 could refer to the state not being in the phase, or it could just refer to our uncertainty in the classification. And the key figure of merit is the sample complexity. So how many samples of the state do you actually need in order to perform this classification with high accuracy? And also, one of the really interesting features of topological order, which makes this problem very challenging, is that topological order is characterized by non-local order parameters, these kind of generalized Gauss laws. And because they're very large, they actually decay very fast, as we'll see, and this results in very high sample complexity. Okay, so I'm going to pause for a second and ask if there's any questions kind of on the setup of the problem that we're thinking about. Okay, great. So let's kind of get into the main core of the talk now. So I'll go through the talk in 4 parts, and let's just dive into it. So first I'll talk about what is topological order. And the key example that we're going to use is what's known as the toric code model. So the toric code model consists of a model defined on a lattice, where you put qubits on the links of your lattice. And you have 2 different types of terms in your Hamiltonian, what we'll call vertex stabilizers and plaquette stabilizers. And in particular, the ground state corresponds to the state where all the vertex and plaquette stabilizers evaluate to +1. Now, this is an example of Z2 topological order because you have a qubit on each site. So you can think about it as a Z2 degree of freedom. And the ground state actually corresponds to an equal weight superposition over all loop configurations. So what do I mean by that? Well, you can think about, let's close this. Okay, well, sorry for you guys, but you can kind of see the loop configuration is just like a configuration where you have like a bunch of, say, pluses and minuses. And anytime you have a minus, the minuses always form closed loops. And the ground state is actually an equal weight superposition over all of these different closed loop configurations. So good. And another way of saying this is that all of these vertex and plaquette stabilizers, they evaluate to +1. Okay, so next we'll talk a little bit about the excitations. So we're going to talk about vertex violations and plaquette violations, states where those terms evaluate to +1. And these correspond to E anyons and M anyons. So the operator that we can apply to create an M anyon is a string of X operators. In particular, you can see that if you apply the string of X operators here, it anti-commutes with the Z stabilizer supported around this ring here and flips the sign of the Z stabilizer. And so because it flips the sign of the Z stabilizer, it carries energy over. Equivalently, we can think about the other operator, the one that creates excitations on the vertices. These are generated by strings of Z's. And these strings of Z operators flip the X stabilizers here. Another thing that's important to note is that, we can actually detect this energy here by winding an n-anion around the vertex, right? So like this X stabilizer can also be understood as creating a pair of m-anions, winding it around the vertex, and then re-annihilating it. And that process actually like will pick up a -1 phase if and only if we have like a charge enclosed. So you can kind of see this manifestation of the Gauss law here in a very simple way. And this kind of generalizes to larger loop operators as well. So the stabilizer you can just think of as the smallest loop operator. But you can look at larger loop operators too, and this thing will basically detect whether there's an even or odd number of charges enclosed within the loop. Okay, so lightning quick overview of the toric code. Any questions about this?
Actually, earlier when you say topological order,
yeah,
you point out this high sample complexity.
Yes.
Actually, can you clarify this point?
Yes, actually, so that's a really good question, and we'll actually get to that in the next 2 slides. Yeah, we'll see like very concretely why the high sample complexity comes from the non-local order parameter. Okay, good. So I think actually let's go straight to that part. So okay, so next let's consider the toric code with a realistic perturbation, like finite magnetic fields, concretely like xi operators and zi operators. These things are going to generate, these are the creation operators for open loops, or e anions and m anions. And as a result, they create in the ground state some finite density of anions, just like in the transverse field in the Ising bundle. For those of you who are experts on this type of thing, you can also think about adding these operators as taking your Z2K theory and coupling it to some scalar matter that lives in the vertices. So you're allowed to have a finite density of matter excitations now. And there's kind of a famous phase diagram for this model where you have some finite robustness to these perturbations. And within this entire region here, the phase is still topological. But then if you go far enough away, if you make these fields large enough, then you have a phase transition out of the topological phase. Great. So, okay, good. So next we'll kind of discuss what are kind of like the caricatures or RG fixed points of the different states in this phase diagram. In the topological phase, the closed loop operators will measure to 1, because if you apply the closed loop operator, like say at the toric code point, it doesn't change the state. However, if you apply an open loop operator, it does change the state, because there's a gap to these E and N anions. In contrast, if you make the HX field infinitely large, then now all of the X operators will value to 1, but all the Z operators will value to 0. So both the X closed and open loops will value to 1, but the Z closed and open loops will both value to 0. And the picture is flipped if you go all the way to the Z paramagnetic phase. Okay, so now to get to Jubin's question, how do we think about states that are a finite distance away from the RG fixed point, but still in the topological phase? So these states, you can actually think about them as being adiabatically connected to the RG fixed point, meaning that there's some gapped path that I can move along such that the ground state remains the ground state. So there's actually some nice work that shows that if you're just moving along within the same phase, you can actually construct a quasi-local unitary that takes the original state and maps it to the state here, somewhere else in the phase. And what this does to our loop operators, our Wilson loop operators, is that it'll take the Wilson loop and spread it out some finite distance. And this distance that it spreads it out is roughly the correlation length of the phase. So because now the loop operator is a little bit spread out, what this implies is that if I measure the original Wilson loop operator, this original Wilson loop operator is going to decay exponentially with the length of a loop. So there's kind of 2 complementary pictures of thinking about this. One of these pictures tells us that when I apply this finite depth local unitary, I create a finite density of virtual anion fluctuations. If these anion fluctuations cross my loop, they'll flip its value and scramble it. And the probability that essentially like the phase space, of course, can flip the loop scales with the perimeter of the loop. Another picture is that the true Wilson loop operator is actually now a dressed operator supported on this finite width annulus. And the bare Wilson loop operator that we're measuring has exponentially small overlap with the true Wilson loop operator. And in particular, that overlap decays exponentially with the perimeter of the loop. So because the signal associated with the Wilson loop operator is decaying exponentially with system size, that's what we mean when we say we have high sample complexity for characterizing the space. Because the signal that we're trying to detect corresponding to the Wilson loops is exponentially small. So does that kind of make sense? Okay, fantastic. Good. So there's this really nice paper from Hastings and Wen, which is essentially kind of shows how to construct these unitaries, which essentially kind of shows how to construct these unitaries. And the key takeaway actually is that in the topological phase, you kind of have a perimeter law for generic loop operators. But unfortunately, this perimeter law also is generic for loop operators in the trivial phases as well. So actually, even the perimeter law decay on its own is not enough to characterize whether our phase is topological or not topological. Instead, what we need are access to these zero law loop operators, these kind of dress Wilson loop operators that don't decay with distance, but instead can go asymptotically to L goes to infinity while maintaining some constant non-zero value. And that's really what we mean when we say non-local order parameter. It's the existence, it's this thing that detects long-range order, but kind of remains constant as L goes to infinity. Okay. Yeah.
If it satisfies perimeter law when it goes to infinity, why is not decaying to zero?
Good. So the bare Wilson loop satisfies perimeter law, but the key takeaway of this Hastings paper is that there's also a zero law operator. In particular, this operator that's supported on an annulus. And that annulus operator won't decay to doesn't satisfy perimeter law, it satisfies zero law. So it doesn't decay as you increase the size.
Oh, it's not decreasing, but it's called zero.
Yeah, so it's zero because it's like the scaling with L, so it's like zero law, perimeter law, area law would be like 0 L squared. Yeah, exactly. Yeah. And yeah, so that's kind of like this is like the true order parameter, the thing that we really want to measure. And you can think about it as like coming from the fixed point dressed by this quasi-local unitary. Good question. More questions? Also, thanks, Julian, for the okay, cool. So let's keep going. So there's other ways that people have discussed identifying topological order that can kind of handle this finite density of fluctuations. In particular, people have talked about measuring the topological entanglement entropy. Now, the topological entanglement entropy requires measuring for regions, the entropy of each region, and then kind of taking the difference of these quantities. However, this observable also has really, really high sample complexity when you're looking at large regions. In particular, to measure the entropy, the entropy requires taking the log of a very small number, and then not only that, you're also taking the difference between these logs of these very small numbers. So this is actually measuring this is very hard in practice. There's also other works that have studied the problem of detecting topological order. So in addition to measuring the topological entanglement entropy, people have also suggested that we can use disorder parameters. So this is by taking ratios of closed and open loops. However, these also suffer from the same sample complexity issue. You're trying to take the ratio of two things that are fundamentally small. People have also used kind of variational algorithms to try to find these zero law operators. In particular, there's some really nice works using tensor network methods to do this, but actually the procedure for finding these variational loop operators in a real experiment from some data, that's actually also challenging and hasn't been done yet. Instead, the approach that we're going to take today is to generate an RG flow towards the toric code state as a way of amplifying the signal from this bare Wilson loop operators. So by going closer and closer to the toric code state, we're measuring the correct operator better and better. And that's going to be our approach for detecting topological order. Great. So the method that we're describing is called local error declaration. And the way it works goes as follows. Imagine you take a picture of the system such that you can identify where all of the anyons live. The anyons are going to be denoted by these like red dots. Let's just think about the anyons for in the first step, okay, so, and importantly, these anyons here all correspond to fluctuations. And these fluctuations are always going to be local, as long as we still remain in the topological space. And that'll be kind of a recurring theme. So these fluctuations are local, and actually from the point of view of an error correcting code, if we think about the ground state as an error correcting code, these fluctuations look like errors above the ground state. And because they look like errors, we can apply like some simple local error correction as a way of removing these fluctuations. In particular, we can just look at anyons and say, if there's two anyons that are next to each other, just pair them up. So it's a little bit like minimally perfect matching, if you guys know a little bit about error correction. However, we're only going to pair up nearest neighbor anyons, not any anyons that are farther away. Then once we pair these anyons up, then we are going to do some coarse graining, kind of like an RG. We're going to take our lattice and split it in half to get a larger lattice. And then we will repeat the procedure. So now originally a distance 2 error at the beginning turns into a distance 1 error after doing the coarse graining, and then gets removed by the subsequent local error correction. And we repeat this procedure a few times, and then measure the bare Wilson loop operator, the one corresponding to the fixed point. And we see that even though this original state was noisy, after doing this procedure, the bare Wilson loop operator gives us an expectation value close to 1. So how do we interpret this? Well, if we kind of reverse the procedure in a Heisenberg-like picture, then essentially what we're measuring is kind of a coarse-grained loop operator that's also supported on the annulus on the original noisy state. And so that's what we call this coarsened or decorated Wilson loop. It's the Wilson loop operator decorated by some amount of local error correction. And what we're going to kind of see is that in our numerics and in our kind of theoretical understanding, these decorated loop operators oftentimes seem to obey something like a zero law for a large chunk of the topological phase away from the fixed point. Okay, so any questions about the procedure? Or motivation of things? Yeah.
So you don't actually remove or drop any qubits. You just measure a larger or bigger operator in the procedure, or do you have to actually throw away something?
This is okay. Good question. So you can really think about it as measuring a larger operator on the original state. So there's no qubits that we're like invisible to, if that makes sense. So like an error on any qubit would appear in the final observable. However, when we do this coarse graining step, we kind of group chunks of qubits together and then like kind of in theory replace them with one qubit. So like a qubit after coarse graining corresponds to like an aggregation of a chunk of qubits at a lower layer. So like an anyon that was like here in a lower layer will still propagate up to the higher layers. So the coarse graining is done so that you don't discard any anyons. You only chunk qubits together. Yeah, so it kind of preserves the structure of the errors. Yeah. Does that make sense?
Yeah.
Okay.
I have a question.
Yeah.
So does this method work all the way down to the transition point?
So we'll see this in numerics, and the answer is no. This procedure essentially takes a region around the RG fixed point, and that entire region is classifiable as topological using this procedure. However, it doesn't seem to go all the way to the phase boundary. Actually, we think that there's fundamental reasons why a procedure like this won't be able to ever saturate the phase boundary. In particular, like, and I guess I'll say this right now, but we can come back to it again a little bit later. Topological order should be robust to kind of any local perturbation. However, you can use local perturbations to like essentially totally scramble the basis that you're measuring in. So like the key is that this observable actually doesn't require any feedback or adaptivity from the input state. And so if we scramble the basis, then we have no way of detecting the topological order using a single basis measurement. So fundamentally, we think that any linear observable like this, a single operator that we measure can't detect topological order in the entire phase. The best we can do is just expand the region that we can classify as topologically ordered, using a linear observable. Does that answer your question?
Yeah, thank you.
Yeah, thanks for the question. Okay, cool, more questions?
This one.
Oh, is it possible to create bigger errors in this coarse graining procedure? Fantastic question. And the answer is, I think the answer is no. And actually part of the reason why the answer is no is because the correction operations that we do are strictly chosen to be local. So if we were allowing non-local correction, then we totally could create bigger errors. But because we require local correction, we can essentially show that for any like local error in the input state, we're eventually going to remove that local error. Yeah. So the locality in the correction step is important for making sure that we don't amplify errors too much. Good. Okay, so let's keep going. Good. So we have this procedure, and now the way that we're going to detect the topological order is essentially by looking at the flow of the Wilson loop observable as we increase the number of LED steps. And in the topological phase, it should flow to 1. And in trivial phases, it should flow to 0, or if it's already at 0, it should stay at 0. The key parameters that we're going to look at are the correction distance. So effectively how, like essentially the width of the annulus, and then the size of the loop. So to check this procedure in numerics, we're going to study a simple toy model where we take the toric code fixed point state and apply this non-unitary perturbation to it that creates some fluctuations in the state. And we know that in this model, there's actually also a phase transition from topological to an X paramagnet at this dashed line location. And when we apply the procedure to it, this local pairing plus coarse graining, we see that in the topological phase, as we apply the procedure, the signal gets amplified to 1 quite quickly. But in the trivial phase, the signal remains at 0. And I kind of want to note actually that this large dark blue line corresponds to measuring like a 40 by 40 loop. Whereas the original light blue line corresponds to measuring like a 5 by 5 loop, a 5 by 5 variable signal. So you can see that we're also increasing the length scale that we're probing here. So the fact that the signal is being amplified to 1 is actually quite remarkable because the original 40 by 40 loop would be like essentially 0 by the time you get to that point. We can also look at the behavior of open loops. Open loops are the things that are non-zero in the disordered phase or the trivial phase. And here we see open loops get amplified in the disordered phase. They remain at 0 in the topological phase. But interestingly enough, these disordered loops don't get amplified to 1, but to some finite value. You can actually understand this as like the endpoints of the loops, are decaying due to a finite rate of closed loops in the background state, and our procedure doesn't remove closed loops, right? It's designed to remove open loops. So it corrects the middle of an open string, but it doesn't correct the endpoints of the open string because it's designed to classify the topological phase, not the trivial phase. And so we do see some amplification, but not amplification to 1. And that's because the procedure was designed for the topological phase. Okay, so these are some simple numerics along 1D cuts. We can also apply the same procedure to the full 2D phase diagram. And here we see kind of the key feature, which is that the region that we can classify confidently as topological grows very significantly under this procedure. Okay. So any questions on the numerical demonstration? Yes.
So if your Gx and Gz are imaginary number, do you see similar result, or doesn't your Z operator you expect to change?
Yeah, okay, so also a really good question. So let's say Gx and Gz are imaginary, so now this is a unitary rotation. If Gx and Gz are small enough, then we know that this thing will create a low density of errors in the input state. And as long as the density of errors is low, we're going to be like below some correction threshold. And we will be able to classify this state as topological. But once this Gx and Gz become very large, then from the point of view of our Z basis and X basis measurements, the error rate is going to become very high. So for example, if you do like, a 45-degree rotation, then like the error density is, like 12% or something. And that's like way above the correction threshold. So there's no chance that we'd ever be able to classify this topological using a correction procedure in a single basis.
But I also see this amplifying feature even when you choose the dimension.
That's right, yeah. So you'll also see like a small region where gx and gz are small will be amplified, for sure. Yeah, good question.
Hi, Nishad, can you hear me? This is Una Kim
Yeah.
from
Hey.
Zoom. Hi. So I was kind of late and I probably missed the important point. But
Yeah.
if I may ask a question, so
Yeah.
what do you think is causing this these errors? What do you have in mind as a source of these errors? So my understanding is that you have the ground state, topological ground state in mind.
Yeah.
And then you are generating these errors, quote unquote errors, by having this operation done to the ground state, right? With your GX and GZ. Okay, so what would be the cause of these errors?
Yeah, so it's a really good question. Actually, there's a variety of different places where these errors could occur in a real experiment. So here, so far, we're just thinking about pure states. And so so kind of here, the way that we should think about these errors are additional terms in our Hamiltonian that appear that we don't have control over. You know, so experimentally, sometimes we can realize a topological phase, but realizing the fixed point of the topological phase is much, much harder. So, you know, we'd ideally like to be able to classify the phase as topological, even if we don't realize the fixed point state, but a state that's just in the topological phase. And so that's kind of what you should be thinking about here in this pure state example. Actually, we'll very shortly go to like a mixed state example where even finite rates of, say, bit flip, phase flip, dephasing, spontaneous emission errors, all of these things can also be partially corrected using this technique. So the technique is actually quite general and applies for like a variety of ubiquitous experimental errors. Yeah.
I see. So here you're thinking about how your pure state is deviating from the fixed point pure state.
Exactly.
So the idea is that the phase might be the same, but wave function can be different.
Exactly.
And the difference in the wave function will be these errors.
Yep, that's right.
Okay. All right. Thank you.
Yeah, for sure. Yeah. And so kind of the key thing again is that like because we're in the same phase, these errors are all going to be local. So because these errors are local, we can correct them using local error correction. Yeah. Okay, great. So any other questions? Okay, so let's kind of get into some of the more ambitious stuff. So actually next we'll talk a little bit about how we can use this technique to classify topological order in mixed states as well. Let's now consider, again, the toric state, but we'll add some bit flipper dephasing error channel to the state. We know from error correction that you know, if the probability of a bit flipper phase flip is very high, above this kind of 11% memory threshold, then we lose access to, then the state should kind of be classified as disordered because we no longer are able to like protect our encoded logical qubit. If that didn't make any sense, that's kind of okay. The key thing is just to note that there's some intuition that tells us that for enough bit flip and phase flip errors, we should lose the topological phase. We kind of studied this problem in by first just looking at the behavior of the bare open and closed loops. So you can kind of see that in the topological phase, the disordered phase and the paramagnet phase, closed loops kind of decay exponentially with the perimeter. When we look at open loops are only non-zero in the kind of paramagnet phase, in the trivial phase. However, these open loops actually kind of are zero and stay at zero, even in the disordered phase too. So what this actually tells us is that it's really difficult to distinguish between the ordered phase and the disordered phase, just by looking at combinations of bare open and closed loops. In particular, for those of you who are kind of familiar with this FM disorder parameter, you know, the disorder parameter kind of relies on distinguishing paramagnet and topological by comparing like the ratio of open loops to closed loops. However, this ratio of open loops to closed loops is going to be zero in the disordered phase as well, with high error rate. So the disorder parameter actually doesn't work anymore when you have incoherent errors. However, we can apply our procedure to kind of a mixed state phase diagram, where on one axis we increase the probability of this bit flip or phase flip. And then on the other axis, we increase the probability of this kind of transverse field coherent type perturbation. And we see that, if we look at uncorrected loops, there's kind of this large region classified as topological, but you can only confidently classify it as topological very close to 0. However, when we apply our procedure, this region that's confidently classifiable as topological grows quite significantly. Okay, so questions on the setup? And
this is again, mixed state. Do you envision having mixed state because of finite temperature, or how should I think about what gives you a mixed state? I understood what gives you different pure state. Right.
Okay, so we will discuss finite temperature in one sec, but the story actually for finite temperature is very different, as I'm sure you are aware. I got very sharp question, because you're kind of predicting that. Yeah, exactly. For finite temperature is very different. Here specifically, we're really thinking about incoherent errors that are local as well. So these local errors, bit flip and dephasing, are the ones that we're considering on this slide. Yeah. So experimentally, these are things that come from spontaneous emission, for example. So we expect those types of errors to have this local structure. And the reason why this works really relies on that local structure. So these are local errors on this slide. And then we'll talk about finite temperature next.
So does the experimental system should I think of it as only having local errors, or could it also be a finite temperature? Is there a way to know?
So actually, I think LED is kind of one way where we can start to tease these two things apart, actually, yeah. And so we'll kind of see in a very nice example on the next slide or two how in the effect of finite temperature actually reflects very differently on these LED observables.
I see. Very cool. Thank you.
Yeah. Thanks for the question. Yeah.
I had a quick question, also on Zoom here.
Yeah.
How do you define confident? That you're confident in this? At what point do you decide you're confident you're in a topological phase?
Okay.
When are you not?
Yeah, amazing question. So really, the way to think about this is what we call the sample complexity. So really, the question is, how many samples do you need in order to be confident? And so we can think about it kind of in the statistics sense. How many samples do you need to be able to say with 95% confidence that you have non-zero signal in your Wilson loop observables? And so in these plots right here, that's essentially reflected in the darkness of the color. So the darker the color is, the fewer samples you need in order to be able to confidently say I have non-zero signal in my Wilson loop observables.
I see. And is there a qualitative difference in the bounds, or how many shots, how it scales with, is there a qualitative difference in this confidence between these two approaches? The error corrected and non.
Yeah. So I guess when you do the correction, I guess the other thing that also comes into play is the length scale. So when you do the correction, you can also confidently measure non-zero Wilson loops at larger length scales. And so because you're always trying to certify topological order up to some length scale. If you only measure the system on 10 by 10 scales, then you can't say anything about topological order at length 100. Okay. You can oftentimes, even with the bare loops, measure say distance 0 or distance 1. But then using this procedure, you can actually significantly increase the size of the loops that you can measure.
Yeah.
So
I guess what I'm wondering is how much is significant. I guess that's what my question is. Does it grow the square root of the length, or do you know what I'm trying to say? Is it just a numerical prefactor up front is better, or does it grow?
So you should think about these observables are binary valued, so they're either -1 or +1, and so and the number of samples you need kind of just is 1 over the square root of the variance, roughly speaking. So
okay.
Yeah, so if the signal is very close to 1, actually the variance is also very small. So that's how. So the variance is typically the thing that sets how many samples you need. And because these observables are binary valued, when they're really large, the variance is also very small. So that's kind of why I was just saying if the signal is very large, then the sample complexity is very small, because the variance and the mean here are like linked because they're binary variables. I'm not sure if I was answering your question.
Yeah, I guess maybe we can chat more about this.
Okay,
Another
good.
time, yeah.
Yep. Thanks for the question. Okay. Yeah, right.
Yeah, another question is, maybe you have explained, but I just missed it. Why for the expectation value of Z closed,
Yeah.
why it has larger value in Z paramagnet than in the topological phase?
Oh, that's a really good question. Actually, this is something we kind of generically see, that as we go farther and farther into the paramagnet phase, the closed loop actually just gets better and better along that direction. And I mean, like, I guess the way to see it, or the way I see it, is like when I'm applying this perturbation to the state, it's kind of taking all the spins and rotating them more along Z. So in that sense, it's kind of like amplifying both Z open and Z closed. That kind of makes sense. I think near the phase transition, things like sometimes are non-monotonic, but definitely like as you go deeper and deeper into the Z paramagnet phase, the Z closed loop will also keep going up and up.
So you also have to measure X open to, sorry, X close to, but
Yes.
It's not plotted.
No, that's right. I mean, so like, of course, X closed is going to be 0 here too. We kind of just plotted a pair because you can think about the other pair just by like conjugating everything. So X closed is like 0 in the Z paramagnet, non-zero in the X paramagnet. Yeah. We were trying not to put too many curves. Yeah. And I mean, but the key reason why like the disorder parameter doesn't work actually is because even in like these paramagnet phases, you have like really the key is that the open loop doesn't have signal anymore. Like usually when you go from topological to trivial, like paramagnet, the open loop gets amplified. The open loop becomes non-zero. However, when you go from topological to like disorder using this incoherent errors, the open loop doesn't get amplified. So you can no longer distinguish these two things just by looking at open loops and closed loops together. The open loops like don't add any more information. That's kind of the message. Yeah. Okay, cool. Thanks for the question. Any more questions?
Sorry, when you say disorder,
yeah.
Can you clarify? I think earlier you said it includes both the open and closed loops, but just make sure why do you say this disorder?
Good. So okay, so specifically now when I talk about, yeah, you're right. This is actually very confusing because there's two different meanings of the two words disorder here. So when I have large rate of incoherent errors, we're going to say this takes us to a decoherence dominated disorder phase. However, when you're in a Z paramagnet or X paramagnet, that's kind of like a trivial phase that like doesn't have topological order. So specifically, what I'm saying is that the open loops don't allow you to detect this decoherence dominated disorder phase. Yeah. And so kind of the key now is that if you just look at the Z closed loops, right, both of them seem like they're decaying like perimeter law in the topological phase and this decoherence dominated disorder phase. And so they both have the same qualitative behavior if you just measure like the bare loops. So we somehow have some way of distinguishing these two things. And the key is that the way that like there's two different types of perimeter law. One of them corresponds to a perimeter law that is correctable by local error correction. The other one corresponds to a perimeter law that's fundamentally uncorrectable. And so when you go from this correctable to uncorrectable regime, that's when you go from topological to like decoherence dominated disorder. Does that kind of make sense? Okay. Also, yeah, if anything's confusing, definitely ask more questions. I think that's the advantage of an hour and a half. We can ask lots of questions. Okay, great. So then the other thing to note also is like something that's kind of important and kind of direction for future study is that this local error correction doesn't actually saturate the error correction threshold. So I told you guys this threshold is supposed to be around 11%. However, we clearly see that when we do this LEC behavior, it kind of saturates closer to 7%. So we're not getting the phase boundary correct. So there's kind of an interesting question here, which is like, what do we need to do in order to get the phase boundary correct? Can we extend these techniques all the way to the phase boundary? And I think this is kind of actually like an open question that deserves further study here. Really, the only statement that we're making is that we can amplify the region that's classified as topological. And we'll actually show using experimental data that this actually is somewhat useful in experimental contexts. Okay. So next, let me talk about finite temperature. So finite temperature is fundamentally a very different type of mixed state that you can encounter. In particular, in 2 dimensions, when you have a finite temperature, you actually lose topological order. So we can, this is also very relevant for experiments where you do, like, say, a finite rate adiabatic state preparation, because we know that the finite rate adiabatic state preparation will also create some errors that look a little bit like finite temperature. You kind of can't cool the state all the way to 0. And the way this is going to be reflected in LED is that it's going to lead to some type of non-monotonic flow of our LED loops under correction. In particular, we can do some simple numerics on the toric code where we simulate a finite rate of incoherent error, of finite temperature, along with some amounts of incoherent error. So we have both incoherent error and finite temperature in the system. As we look at the flow of the Z closed loops under the LED procedure, we see that at early layers, the loops kind of get amplified. However, for any finite rate of finite temperature, eventually these curves are all going to turn around and head back towards 0. And the intuition is that when you have finite temperature in these systems whose ground states are topologically ordered, this leads to a low density of anyons that are uncorrelated with each other. And because they're uncorrelated, they're uncorrectable by the local pairing procedure, by this local error correction. And so this finite density of uncorrectable anyons, uncorrelated uncorrectable anyons, builds up over time as you do this local correction and coarse graining. And it's this buildup of the density of anyons due to the coarse graining step that causes this to eventually turn around and go back towards 0. So finite temperature errors look very different than local incoherent errors.
Yeah, can you explain again what you mean by uncorrelated anion?
Okay, fantastic. So how do we think about a finite temperature state? Well, a finite temperature state, essentially configurations are weighted just by the energy that they contribute, right? So, these topologically ordered phases are deconfined in the sense that the energy of a pair of anyons doesn't depend on the distance between the anyons. So in a finite temperature state, we have kind of equal probability associated with 2 anyons, that are like distance L over 2 apart, or else the system size. So like, as far apart as possible, and like right next to each other. And so that's what I mean by uncorrelated, essentially. Because the only energy penalty comes from the energy of the anyon's positions are no longer going to be like linked together. They're going to be like totally far apart, like just randomly distributed throughout the lattice. This is in sharp contrast to like when you take a ground state and you apply a Hamiltonian perturbation, because there the distance between the anyons actually does determine kind of the probability weight. If you think about it just in terms of perturbation theory and dressing, if I wanted to create like a pair of anyons distance L apart, I need to do L off resonance flips. And so that's going to kind of come in as like, your H to the L over your stabilizer energy scale to the L minus 1. Yeah.
So would this would your procedure work if you went to some model where you had weights to the anion strings, or?
Yeah, so this is a really good question. And I guess I would say that if you actually had a model where the anion strings had enough weight that the anions now were like would not uncorrelate at finite temperature, then you'd have a model with like a finite temperature phase transition. And so actually, like as long as you're below the finite temperature phase transition, then you would still see like correlated anions, and we would correct those. But the reason we're correcting them is because we're below the phase transition and hence the topological phase. Yeah. So like really the key is that, we're distinguishing between correctable anyons and uncorrectable anyons. And we're kind of associating in general these correctable anyons with the topological phase, and these uncorrectable anyons with the things that destroy topological order.
And how do you identify what is correctable? Is it based on distance?
Yeah.
Maybe you can. Yeah.
Good. So like, let's say we have some finite density of uncorrectable anyons, like in this finite temperature case. The way that we can detect this is just by applying the LED procedure many times. If there's a finite density of uncorrectable anyons in the system, eventually our Wilson loops will start to go back towards 0. So I think I would say that's how we're detecting the uncorrectable anyons. We're applying the LED flow, and we're seeing that the flow will eventually turn around and go to 0.
So in other words, you're just going to try it, and if it fails, that tells you that there were uncorrectable ones. Is that another way to think of it?
Yeah, exactly. Yeah.
Okay.
So I guess to maybe make it a little bit more precise, we will say that if there is a finite rate of uncorrectable anyons, then there is no LED procedure that will flow to 1. Yeah, because the statement we're always making is that we have a positive signature for the phase, so we can have a witness for topological order. But if it flows to 0, it could flow to 0 for many different reasons. Yeah. So uncorrectable anyons are one reason it could flow to 0. Measuring in the wrong basis is another reason it could flow to 0, for example.
An experiment presumably has mixed state due to sort of local errors, but also finite temperature looking errors.
Yeah. So whenever we apply this in a practical setting, the specific statement that we're going to make is that we can correct errors, that we can detect topological order up to some length scale. So let's take this simple example here, right? We see that the signal increases from 0 to 1. Actually, this tells us that the system looks topologically ordered at short lengths. It's only at really long length scales, when these uncorrectable anyons start to build up, that the system starts to look not topologically ordered. So there's actually this additional parameter, which is what distance can you certify your order up to? And so whenever we talk about a real experiment, we're only going to be trying to make a statement of that sort. Yeah, that we're seeing some semblance of topological order up to some length scale.
Then if I have to ask a very uncomfortable question, has the topological order been seen in experiments?
It's a good question. I mean, I think
up to some distance, it's been seen.
Up to some distance, I would say the answer is yes. Yeah, up to some distance. Now, we can get into this discussion a little bit at the end, maybe. But here we're only certifying topological order of a state. So specifically, we're certifying the long-range entanglement in a state. So this doesn't really tell us anything about whether we're in a topologically ordered phase, which has the right excitation structure and things. Yeah. So specifically, we're certifying long-range topological order in the state that is experimentally prepared. Yeah. And I will say that none of our experimental results satisfy. Essentially, all the values are still so small that we wouldn't be able to rigorously certify topological order up to any length scale using those experimental numbers. Yeah. In the spin liquid experiment, if you are interested just in a general though, these circuit-based constructions where we prepare toric codes using circuits, those numbers are actually extremely high. So topological order has been prepared in an experiment. Specifically these toric code experiments.
Has or has not.
All right, thank you.
Yeah.
Has or has not.
I would say the answer is yes, but we can maybe talk about it when we look at the data. Yeah.
This is numerical simulation.
This is all numerical simulations in the toric code. Yeah. Good. Okay, so let's talk about experiments. Oh yeah,
Okay. Just one more question.
Yeah.
In your numerics, you always do with a finite size system, right?
Yeah.
If you're a very small temperature below this temperature, that your protocol just works, or as soon as you turn off even a little bit temperature in your numerics, you still see this turnover.
Okay, really good question. So I guess we're always working in the limit. So like if I show LED going up to 4 here, and I'm probably like plotting some like 5 by 5 loop after L equals 4, after N equals 4, the system size is like at least 2 times bigger than the largest loop I'm probing. So we haven't really studied the regime where like we like look at small system size and like lower the temperature. But of course, if you think about this intuition about temperature as setting the length scale at which you lose topological order, I kind of agree with your intuition that like for small enough temperature, you should still have topologically order in like a finite set system. Because we also kind of agree that the temperature will set the length scale at which you lose topological order.
Yeah, because if in the actual experiment the temperature is not so high, then the protocol is still very useful.
Yeah, yeah. So in the real experiment, like actually, I think even in an infinitely large lattice, the finite rate of our adiabatic sweep is going to set the length scale, like fundamentally the length scale that we can prepare order at. Yeah, because if you want to prepare infinitely long range order, you need to go infinitely slow, and that's kind of like a fundamental limit. Good. Okay, so let's talk a little bit about the experimental results. So specifically, I'm going to discuss this kind of resonating valence bond model on the Ruby lattice, and we're going to study this, in the Rydberg system. And in the Rydberg system, the dimer constraint associated with resonating valence bond states is kind of naturally encoded by the Rydberg blockade. So there's some actually really nice theory and experimental work on this model, and kind of the key theoretical insight was that if you take the Ruby lattice and place the Rydberg atoms in the link, and you can, and then you have some finite blockade radius. So essentially, in these Rydberg systems, you have very strong Rydberg-Rydberg interactions, and these energetically prevent you from simultaneously occupying any 2 sites that are kind of within this red circle here. So you can kind of think about this as enforcing a constraint on your Hilbert space that I will never have any states where 2 sites within a blockade radius are simultaneously occupied. This constraint maps onto a dimer constraint, where I can take each one of these links, put a dimer on it, just some object that intersects with the vertices, and the dimer constraint essentially says that I can never have 2 vertices that both have a dimer on it. It turns out that these dimer states, a superposition over all dimer states, is another way of realizing Z2 topological order. In particular, you have M anyons that live on kind of the hexagons of this model, and the strings that create the M anyons are again something that measure the parity of the dimers along a string in the system. The E anyons, which live at the vertices, essentially measure whether or not the vertex has, 1 dimer on it or a different number of dimers on it. And in particular, in the topologically ordered state, the fixed point state, every vertex should have exactly 1 dimer on it. So it should be like a dimer covering. And the operators that create these E anyons are essentially operators that shuffle dimers around and remove them from the state. So when you apply this operator to the state here, at the end you're left with like 2 holes where you have 2 vertices that don't have an anion on them, that don't have 1 dimer on them, and we interpret this as like a pair of E anyons. Okay, so the experimental system that was prepared was on a lattice of this size. And specifically, we're going to look at some very large Z loops that are approximately this big. And we're going to apply kind of 3 different layers of correction of these Z loops. So for the same loop, when we look at like the D equals 0 version, the bare uncorrected version, you kind of can't see any signal reliably across this phase diagram that was prepared. When we apply 1 layer of correction, it's still pretty hard to see anything, but maybe if you really squint your eyes, you can start to see some small fluctuations that are non-zero. However, when we apply 2 layers of correction, we see a sharp jump actually in the order when we go from this kind of around 3.4, which seems to signify that there's some ordering associated with this these kind of coarse-grained loops here. We can also study the open Z strings at the same time. And when we look at the open Z strings, we see that the signal kind of remains close to 0 for all 3 of these loops that we studied. So like t equals 0, t equals 1, and t equals 2. We can also look at X loops. So again, we look at an X loop that's quite large compared to the size of the system. And the X loop signal looks as follows. So in the regime from 1 to around 3.5, we see that the X loop signal gets amplified quite a bit. Then if we look at the corresponding open loop signal, we actually see that, again, in the same region from 1 to 2.5, the open loop signal is also getting amplified. However, there is a large region, this region 3, where the closed loop signal is getting amplified, while the open loop signal is not getting amplified. So if we take all of these things together, these 4 different observables, we can kind of assign like a classification to the 4 different regimes that we see in this experiment. In the first regime, where the open Z strings are being amplified, but nothing else is, it looks like a Z paramagnet. In the second regime, where both X and open and closed strings are being amplified, but both Z open and closed strings are not being amplified, this looks like an X paramagnet state. However, in this region 3, where we see both closed loops are being amplified, while none of the open loops are being amplified, that's most consistent with the spin liquid regime. And kind of our last classification is for this region 4. So we see that the farther we go from region 3 to region 4, the kind of less and less these X open loops these X closed loops are being amplified. And in particular, by the time we get all the way to 6, there's no detectable amplification in the X closed loops. However, this is happening without any amplification of the open loops as well, right? So actually, this is most consistent with like a high rate of incoherent errors in the system accumulating over time. Because if this was consistent with what was previously believed to be true, that as we're increasing the detuning, we're going farther and farther into a valence bond solid phase, then we would also expect some non-zero signal appearing in the open Z strings. However, because we don't see any non-zero signal appearing in the open Z strings, we conclude that this effect is most consistent with kind of a decoherence dominated disorder phase. Okay, so any questions on experimental analysis?
Actually, 2 slides earlier, you show on the bottom of this M string or M loop,
Yeah.
you get a phase. I think it's not -1, but e to the power minus I alpha.
Okay, good. So it actually turns, okay, so it is kind of a very technical detail, but it turns out that there's 2 different ways to realize this thing. Essentially, if we really stare at this thing here, we see that the effect of this loop operator was to flip this dimer from this side to this side. And actually, when you flip this dimer, you can, there's like 2 different realizations of the state. One where you pick up a phase, and one where you like don't pick up any phase. And so the alpha here just kind of encodes that, like, depending on which one of these states you happen to realize, you'll either get a phase or won't get a phase. Yeah. And actually,
you'll be plus or minus 1 still. Plus 1 or minus 1.
Yes, I think that's right. Yeah. Don't quote me on that, but I think that's correct.
I had a question. So you told us earlier that just looking at open and closed loops wasn't sort of enough for complete understanding. Did you apply your error correction scheme thing to study the data? Is that not possible?
No, so that's exactly what we did here. So essentially, the different curves correspond to different amounts of error correction.
I see.
And like, exactly. So if we just look at the signature of the closed and open loops, without any correction, those are kind of the blue lines. And just looking at the blue lines, it's really hard to see any signal at these length scales. However, by applying the error correction, a few things happened. First and foremost, we were able to see signal even at these very long length scales, which is kind of cool. We're able to see signal at a much larger length scale than was previously possible by using this error corrected dressing approach. The second thing that we were able to conclude is that because of the flow of the loops, we didn't see any flow of the loops in this regime. We didn't see any amplification of the closed loops in regime 4. And therefore, we kind of conclude that we've crossed over from this correctable regime to this uncorrectable regime. because even though we're doing correction, it's not doesn't seem to improve anything. And that's why we say this is most consistent with like decoherence-dominated disorder phase.
Yeah, I see. Thanks.
Thanks for the question. Yeah, very well.
What happens to the d equals to 2 curve for the closed X and the open X?
Good. So it's a little funny. Actually, if you look at these strings here, when we do d equals 1 correction, they kind of get coarsened by like the length scale of the hexagon. So there's actually no d equal. We can't do d equals 2 while keeping it in annulus. The loop's not big enough. Yeah, good question. Yeah. It's different for the z's because the length scale is like the little triangle. Yeah.
Here's a question.
Oh. Could you repeat the intuition for why LED does not help with measuring open strings? So LED does actually help with measuring open strings. If you like, so just to go back really quick to the numerics, we actually also do see that in the trivial phase, LED does actually significantly amplify open strings. So that's true just in our simple numerics. And then going back to the experimental data, we also see that LED like amplifies, X open strings in the X paramagnet phase. So actually, like if the open strings aren't being amplified, then that kind of suggests that like it's because there's no ordering in those open strings, or we're in like a spin liquid phase or a decoherence dominated phase where we don't expect these open loops to be amplified. If that makes sense. Does that answer your question? Okay, perfect. Thanks for the question. Cool. More questions? Yes.
Just curious, like what are the Z operators? They seem much noisier than the X. Is that like?
That is a good question. I was also wondering this a little bit, but I did not. I honestly don't. I'm not sure. Yeah, it's a good question. Yeah, I was wondering maybe like the corners play a role or something. I'm honestly not sure. Yeah, that's a good question. Any other questions? Okay, so let's keep going. Great. So now for the last like 15 or so minutes, we can kind of discuss a little bit of like the theoretical foundations of this approach. So I think a very helpful interpretation for what we're doing comes from thinking about these dressed Wilson loops as being a kind of surface code. So we have the original Wilson loop operator. When we dress it by some correction distance d, then now we can think about it as like a Corson Wilson loop operator supported on an annulus. We can think about this annulus as supporting a surface code where we've paired up all errors, that are below the correction distance d. Now, in the surface code picture, in the ground state, we should expect no enclosed anyons, right? Because the ground state, we should always be in the vacuum center when we look at a loop. And in the surface code picture, that corresponds to having being in logical state 0 when we just look at this loop. Now the perimeter law decays with some rate, so it's like e to the minus I alpha L, and this alpha essentially encodes the logical error rate per unit length. Essentially, it's like what's the probability that I have a string that's spanning my logical operator per unit length. And so the uncorrectable and correctable regimes are fundamentally different. And specifically here, I'm talking about imagine there's two different ways of being uncorrectable. One of them comes from this high rate of local incoherent errors, and the other one comes from condensation of the E and M anyons, or these open loops picking up non-zero expectation value as I have a phase transition into the trivial phase. These are two different ways that you can be uncorrectable, and they both manifest in slightly different ways. In the condensation picture, so this is pure states, ground states, these long open strings pick up a non-zero expectation value, and in particular, these non-open strings can kind of span this boundary. So if you have a non-zero expectation value associated with the operator that spans this boundary, then that actually tells you that, you know, your logical operator going this way can't have expectation value 1, right? Because these two things anti-commute. In the surface code picture, you can think about this long open string that spans the boundary as creating a logical error in your surface code because it flips the state of the qubit. In the incoherent side, where you have a very high density of incoherent errors, each incoherent error kind of looks like a very short open string. But as we know, if we create a very high density of short open strings, then when we try to do correction, we can't really distinguish between the two different types of pairings. You know, one pairing gives us the right answer, it takes us back to 0 logical, but the other pairing will give us the wrong answer. It'll take us to 1 logical. So both of these different sources of errors would lead to uncorrectability of our loop operator. And what's nice about the surface code interpretation is that it applies both for pure states and mixed states. Right? So whether it's uncorrectable or correctable actually didn't rely on any features of like the parent Hamiltonian or anything like that. Okay, any questions on surface code interpretation? All right. So another theoretical tool that's pretty helpful is that we can actually construct this LED procedure using local quantum circuits. So this is kind of an approach that was pioneered by Iris, who's kind of my main collaborator on this project, in this quantum convolutional neural network paper from a few years ago. And kind of the key idea is that the quantum circuit essentially does this local error correction that we're discussing today. So, you know, essentially you can think about each of these units here as like, we have qubits, we use these qubits to measure the stabilizers. And then locally, by applying a multi-qubit gate, you take the values of the stabilizers and use them to correct one of the other qubits in your system. So you can actually construct, so here, this is like an example of the transverse Aliasing model, where your circuit essentially implements like a majority book correction. In our 2D case, we didn't draw it because the picture is much more complicated. You can use similar circuits to apply like pairing operators and local pairing operators. And kind of the key is that when you turn this procedure that we described like qualitatively, or computationally, not qualitatively, we described the computation you would do, you can turn that into a quantum circuit that does exactly the same computation. And the key is that the circuit actually preserves locality. So because it preserves locality, you know, again, this picture of coarsening that we described before kind of holds. A local operator measured at the end of the circuit will map onto a larger but still local operator with the same topology at the beginning of the circuit. Okay, so actually there's some nice implications of the circuit construction on kind of the rigorousness of this LED procedure, like the fact that we can show that it like works. You know? So in particular, we can think about the following setting where we have our input state, a bunch of ancillas, and then we apply this local circuit to it. What we can show is that if the state flows to 1, meaning that the Wilson loops flow to 1 as we do this local error correction procedure, then after the local unitary circuit, it has this structure where you've basically prepared the toric code state, tensor a bunch of ancillas that kind of contain the qubits that were removed during coarse graining, and also the qubits that were like involved in the stabilizer measurements. And the fact that you have this local unitary circuit connecting the input state to the output state allows us to make the following statements. First, we can prove pretty straightforwardly that no product state can be classified as correctable under LED. So there's no input state that is locally connected to a product state that would flow to 1 under this type of procedure. And the locality is kind of the key ingredient there. Another statement that we make that's a little bit more subtle is like, let's say the output state now isn't perfect. So we don't measure Wilson loops of 1, but instead we measure Wilson loops that are 1 minus epsilon. What we show is that this implies the input state here cannot be connected to the product state by any local unitary circuit of depth less than epsilon square root 1 over square root of epsilon minus the correction distance d. So kind of the rough intuition is that when you measure like stabilizers as having a small amount of noise, so noise epsilon, this immediately implies that you can't actually create that state using any local circuit of depth less than 1 over square root epsilon. And actually proving why it implies that is a little bit tricky, and it required us to kind of extend some results from Ha on classification of like topological states from a few years ago. And then the minus d comes from the fact that this local unitary circuit can further spread things out by some distance d. This also kind of shows you why, when we were looking at these X loops, we couldn't look at d equals 2. Because if we start to look at d equals 2, then, the fact that there's no interior to the loop anymore means that we're like not really making any claim of, essentially you can get what we call overcorrection, where if you make d much larger than L, then you automatically amplify the signal, but not for the right reason. It's only because you're trivially removing all of the anyons inside the loop. Okay. Good. And then kind of, more future looking, we also are kind of suggesting this type of construction here as a possible definition for what we mean when we're talking about like the mixed state phase that is topological. In particular, the fact that the fixed point wave function is kind of locally distillable from the input state, as these two results show, implies that the input state has some amount of long-range entanglement built into it. So this kind of local distillability is a definition that seems to apply both for the pure state classification. This is kind of actually how, it's based on this generalized local unitary transformation that people have already been using to classify pure states, and it extends it also to the mixed state case, because you can introduce product state ancillas and also remove degrees of freedom here. Okay, so any kind of questions on these statements? Okay, so I'll just keep going, and then we can also have more questions at the end if there's more questions. We can also kind of connect these statements to the entanglement negativity of the mixed states of the input mixed state if we make an additional assumption. In particular, if we can show that this kind of ancillary degrees of freedom that were removed or distilled out, if these are also trivial in the following sense, where it can be prepared from a product state by a local unitary circuit, then we can show that the entanglement negativity has a topological term. In particular, we can show this in the case where these unitaries are like Clifford circuits, because when they're Clifford circuits, it's much easier to compute things. The key is that this here is like a stabilizer state, and if they're Clifford circuits, then this here is also, a stabilizer state with some degrees of freedom traced out. So in that setting, at least, we can show that this LED procedure, if you have LED flowing to 1, then this implies the input state has also like entanglement negativity. So, I think this procedure is also kind of connected to other methods of classifying mixed state in topological order, as some of Rodney's members are experts in. So it also kind of connects to some of those definitions too. Okay, great. Also, just in terms of generalizations, I think one kind of straightforward generalization is to Z2 gauge theory in higher dimensions. In particular, in higher dimensions now, we don't have point-like excitations, but we have like line-like or membrane-like excitations if we go to higher and higher dimensions. You can also straightforwardly generalize this like local pairing rule to these kind of more complicated surfaces. So actually, there's this kind of cool thing called Toombs rule, which allows you to apply local operations and actually contract loops. So the key idea is that you can like detect the curvature of the loop and always kind of contract loops inwards as opposed to outwards. And you can do that just using local operations. Okay, cool. So with that, we talked about topological order, Wilson loops, how they're addressed with perturbations. We constructed this explicit RG flow and saw how we can classify the phases topological in a wider region. We demonstrated this on 2D toric code numerics and also experimental data. Cool. And more generally, we're kind of interested in thinking about this as like a powerful tool for understanding the mixed state phase diagram. We're also kind of working on extensions to other types of topological orders, for example, non-abelian models. We've also been thinking about this basis problem. So, something else that's also kind of interesting is adapting the basis that we measure in dynamically, so that we can kind of correct for arbitrary local rotations. This is this kind of nice result that there's no linear observable that can give you 1 in the entire topological phase, because topological phases are robust to local unitary rotations, but any linear observable can be scrambled by local unitary rotations. So you kind of need some amount of adaptivity or nonlinearity in the observable that you measure. Yeah, I'm also happy to talk about that more if it's more confusing. Okay, fantastic. And then with that, I'd like to thank all of my collaborators. In particular, I really want to emphasize Iris, who's kind of my partner in all of this work and a really amazing person to collaborate with. Also, in particular, Soonwon, who together with Iris kind of developed a lot of this original QCNN work that most of this is built off of. And then, of course, the rest of our amazing collaborators for their help in these endeavors. And to all of you guys for listening. Thank you so much.
Thank you very much. Thank you, Nisha. Any question, comment, or comment questions?
Which non-abelian models are like specific one?
Yeah, so actually, Iris has kind of been pushing this quite a bit. But our current understanding is that it kind of should work for any modular tensor category. And like the rough intuition is that, you can kind of generalize this stabilizer measurement into a procedure where you kind of detect the local anion content.
Mm-hmm.
And then you can generalize this local pairing procedure to essentially trying to probabilistically fuse groups of anions, which have the potential of fusing to the trivial or vacuum center. And by kind of alternating these 2 procedures and also incorporating coarse graining, you can kind of reproduce a lot of the same aspects of the simple toric reconstruction.
We could consider topological order with the current topological order, where there's at least the folklore there's no fixed point wave function with 0 correlation that might bring some difficulty.
So this is a good question, and I'm definitely not an expert in this stuff. But I think at a very high level, we've mostly just been thinking about it at the level of like anionic operations. And so even in the chiral topological order, you have some anions, and as long as you can detect them and try to pair them, everything should kind of.
Let it work with some phenomenological model for the anion. Just deal with anion hopping on some fictitious ladders and then create them up.
Yeah, I think so. We've kind of we have been thinking about it more at the phenomenological level, as opposed to microscopic lattice realization. Yeah, more questions? All right.
Sorry, so you answer to chiral, the topological order with non-zero chiral central charge. Let's say your answer is it could be possible. What's your answer? I didn't get it.
Good question.
You don't know.
So okay, I'm definitely not an expert in this stuff, so I don't know actually. But I think the answer, at least at the level of the phenomenological model and the anion operations, it seems like it could be possible. Yeah, maybe actually you can help us understand some of this stuff. Okay, cool.
Yeah, thank you very much.